The content in this video can be found on pages 49 through 51 of your textbook and is meant to help you achieve learning objective number 11, which is to describe the major components of Earth's annual energy budget. If you haven't already done so, it's a good idea to skim through pages 49 and 51 before you watch the rest of the video and pay particular attention to the figures and their captions. A lot of the figures in this presentation come from web resources that I think I don't spend much time sourcing. Please, though, plan to read the content more thoroughly before you attempt online concept quiz for this chapter. So the title of this presentation is Earth's Energy Budget. And while that topic may seem a little bit dry at first glance, I hope I can convince you that the global energy budget is anything but boring. It's of vital importance because without the correct balance between shortwave energy from the sun and long-wave energy from the earth, life would not be sustainable. Our oceans and our atmosphere are almost entirely responsible for balancing this budget. And through the course of this presentation, I hope to show you in simple terms how that balance is reached, how we know conditions have varied throughout Earth history, what the current condition of the atmospheric budget is, and what the implications are for the near future. And finally, to provide you with an idea or two about how to keep this information organized without being pulled into a non-scientific discussion about climate change. Our goal is, as scientists, after all, should be to make data-driven decisions using the best available science. This slide illustrates the Earth's radiation balance. And there are figures just like it in any geography textbook. And I know there's a figure just like it in your weather book. This one, though, comes from the National Climate Data Center, the NCDC, at NOAA, the National Oceanic and Atmospheric Administration. And it presents one version of the budget. Other versions are virtually the same, with slightly different percentages in the various categories. For now, these are nothing to be concerned about. The orange arrows on the left-hand side of the image show the cascade of shortwave radiation that comes from the sun and ultimately warms the Earth's surface. You'll notice by the relative width of the arrows that a significant portion of that energy is reflected and scattered back into space before it gets to the surface of the Earth. The 63 to 70% that remains is absorbed by the atmosphere and Earth's surface, and it can be said that that energy drives Earth's climate. Looking at the red arrows on the right-hand side of the image, you'll see that the cascade of long-wave energy that comes from the Earth. Everything that has a temperature emits heat. Planets, people, everything. The Earth emits 117 units for every 100 units of incoming solar energy. Most of that energy is absorbed by the atmosphere, which also gets energy from latent and sensible heat. So that's plants and storms and things like that. And also, of course, from some shortwave radiation. Once in the atmosphere, some of the energy is radiated into space, but more of it is back radiated to the surface through the greenhouse effect. When we talk about Earth's heat balance, though, we're really talking about the budget of how much heat comes in, how much heat leaves, and how much is retained in the planet. So when the energy balance at different latitudes is compared, it's possible to see regions of a net surplus and a net deficit. Near the equator, there's a net surplus of energy. So that's in these latitudes here, right? We see all the way up and even beyond the tropic lines an excess. There's a surplus of energy. Shortwave energy from the sun strikes the Earth more directly in that latitudinal belt, resulting in a higher intensity of insolation. Also, cloud cover in the tropics is thick and covers a larger area than in the northern latitudes. For those reasons, shortwave energy entering the Earth's system is greater than the amount of long-wave energy leaving the system. Closer to the poles, you can see an area labeled deficit, so 50 through 90 degrees north and south. Here, the angle of incidence is lower, so that the sun's rays strike the Earth more obliquely and with less intensity. Long-wave energy leaves the system here in higher amounts than short-wave energy can enter. Without some way to even out that regional imbalance, the poles would keep getting colder and colder, and the tropical zone would keep getting warmer and warmer. Oceanic and atmospheric circulation minimize that imbalance, but that difference in energy balance is an important component in the development of ice ages on Earth, for example. The distribution of insolation displayed in the graph on the previous slide is shown on the map in this one. You can see that the hot colors are all distributed between 38 degrees north and south of the equator. These are the areas receiving the most insolation on an annual basis. So wherever you see the red and orange colors, we're looking at that positive, the surplus energy section. As you move towards the poles, from those red and orange zones, you can see the colors are quickly changing from hot colors to cooler ones, showing the steady decrease in insolation. Washington State, Maine, Central Europe, much of China, and the northern end of Japan are all in the yellow zone, which is barely even present in the southern hemisphere, just a tiny amount here at the tip of South America. Aside from parts of New Zealand, parts of New Zealand and and Argentina, notice that the deep red area in Central Asia is surrounded by orange. So here's deep red, and here is the orange ring. So why do we have that bullseye? If you want to pause this presentation and think about it for a minute, I would love to talk more about this in a future discussion. Why do you think the pattern is interrupted there? A hint is in these bullets on the slide. Elevation can also affect insolation. So if we have very tall mountains that reach to the top of the troposphere, we are above the vast majority of air molecules in the atmosphere. So without any real substantive molecules to get in the way of the incoming solar radiation, we get a larger amount of energy from the sun. So that bullseye represents the Himalayas, the world's tallest mountain range. And they do, in elevation, come close to the top of the troposphere. So how about this other question? Why so much more yellow and green in the northern hemisphere? A bit of a visual trick. If you guess that it's because there's more ocean, there is, especially in this band between Antarctica and Australia and South Africa. There's just much more land here for us to have those climates. Water tends to ameliorate those cold climates. About 100 years ago, a Serbian mathematician named Milankovitch became interested in the climatic history of the Earth, and he began to compile astronomical data from great historical scientists to determine the amount of insolation in those northern latitudes, the yellow band, the green band, at different times in Earth's history. He was interested in learning whether Earth's past ice ages could be explained by Earth-Sun relationships, week 1 stuff. To his delight, he discovered that the mathematics involved in developing his model were complicated but straightforward, as I hear mathematicians say. Despite being imprisoned by the Austro-Hungarian army during his honeymoon, which coincided with the onset of World War I, he completed his opus to demonstrate how variations in solar intensity at 65 degrees north were driven by rhythmic changes in Earth's solar orbit, and that they did in fact correlate with Earth's historic ice ages. Milankovitch explained the fluctuations in solar intensity through 3 principal orbital variations: the oval-shaped nature or eccentricity of the orbit around the Sun, which causes the maximum and minimum distance, aphelion and perihelion, to vary over time. And the time scale of that variation, he estimated at approximately 96,000 years. So over 96,000 years, we go from circular to elliptical, and then another 96,000 years later, we go back to circular, or almost circular. The angle of the Earth's tilt, or obliquity, as Milankovitch called it, varies between 22.5 and 24.5 degrees over a 42,000 year cycle. So over 42,000 years, we go from a 22.5 degree tilt to a 24.5 degree tilt. And right now, we're right in the middle at a 23.5. As that change in tilt occurs, that causes a change in the intensity of seasons in both hemispheres. So as we tilt closer to the sun in the northern hemisphere, we would have hotter summers and milder winters, and the southern hemisphere would have colder winters and cool summers. And as the axis tilts more towards the 22.5, we would have cooler winters in the northern hemisphere and cooler summers too. And they would have milder winters and summers in the southern hemisphere. So the third process, which Milankovitch called precession, is sometimes called the wobble of the Earth's axis. It varies over a 26,000 year time scale, so that the north polar axis is oriented at the North Star now, but in 26,000 years it will be pointed towards Vega. That causes the equinoxes to shift on the calendar and the seasonal intensity to change in one hemisphere at a time. All of this Milankovitch discovered with no more than pencil and paper in a library somewhere in Eastern Europe in the 1917 through 19. Chemical traces from proxy data are used to reproduce the paleotemperature record for the Earth. So when you hear people talking with expertise about paleoclimate, the way climate has been in the past, they are not going back and measuring these temperatures with thermometers. There's no time machine that enables them to do that. But what they do is they use what's known as a proxy data. So things like tree rings are an example of proxy data. Remember in that first talk, I showed you the picture of the lumberjacks standing in front of a fallen tree. You can go back hundreds of years measuring the thickness of those rings and determine what the conditions were like. Were they favorable for tree growth or were they not? So this doesn't tell us the real temperature, but it gives us an idea of how generally wet and warm the climate was. So climate proxy data is information about the past climate that substitutes for direct measurements. Because recorded information about these things only really began with any repeatable regularity in the 1800s, we need information from tree rings, from ice cores, from pollen, marine sediments, to reconstruct a historic record of the temperature. One very good way to assemble a historic record of precipitation is through the use of the ratio of two isotopes of oxygen. So this is the D18O, and if you're nodding off as I begin to talk about this, stay awake because this really is kind of exciting. The atmosphere and the ocean contain both of the isotopes, and because O16, its molecular weight 16, is lighter than O18, it's easier for the atmosphere to evaporate from the ocean during times of ice cap growth. And so if we look at the ratio of how much of a sample of oxygen is 16 compared to 18 isotopes, that's known as the D18O or DO18 curve for marine sediments. That when we look at that curve for marine sediment cores, it's exactly opposite from that we find in ice cores. So that when ice caps are growing on Earth during ice ages, air bubbles in glacial ice contain more O16 because they're being selectively evaporated from the oceans. While microfossils during the same events in the tropical oceans contain more O18 because the O16 is being selectively evaporated. During periods of ice melting on Earth, we call these periods interglacials, air bubbles in glacial ice contain less O16. And microfossils in tropical oceans have less O18. And looking at the record, both in marine sediments and ice cores, it takes about 100 to 125,000 years to reach the full extent of an ice age. So here is a high stand in sea level. Here is a very low stand in sea level. So this is an ice age. This is the most recent one that carved most of the topography that we see around the Puget Sound area. This is the most recent one. This is our time now, right? And this is the last warm period between before the current one. And you can see it's, even if it looks a little bit like it might have been a little bit warmer to you, it was. Sea level was a little bit higher 125,000 years ago during stand 5E. But you can see a sawtooth pattern. It takes a long time for us to build up the ice on the ice caps, and then a relatively short time to get rid of them. So an ice age termination occurs every 100,000 years ago, and we're at the very end of one now. So that sawtooth shaped curve gives that 018 curve sort of a unique shape. When we look at the ice core data, we notice that 18O, here's the same trend, right? Here is the oxygen 18 data. We see a high number 125,000 years ago that rivals the one we're experiencing today. We see two different things plotted here, temperature and a CO2. These gray lines are the Milankovitch produced guesses. So they're smooth, right? This one is the 100,000 years. So this is the eccentricity of the orbit. And this one is, sometimes you'll see 20,000 and sometimes 40,000. So this is the precession of equinox's curve. And it's paired up with changes in CO2. So whenever we see high values of CO2 in ice cores and marine sediments, we also see high values in oxygen in the Milankovitch predictions. So this goes back 400,000 years. Here's one that goes back 800,000 years. So in this graph, we're looking at the carbon dioxide parts per million. Very high now, like we mentioned that in other presentations. 20,000 years ago, as the glaciers began to retreat, we know that CO2 was very low. A lot of it trapped in ice in both poles. So the warming trend and the CO2 trend are born to be hand in hand. And it's extremely difficult to look at data at this scale. I couldn't find a curve that showed just, say, 10 or 20,000 years worth of data. If you can, I'd love to see what it looks like. But from what I gather, from the things that I read about the atmosphere and paleoclimate, is that the CO2 curve lags behind the global temperature by about 100 years. That means the warming happens first, and then comes the CO2 throughout the last 800,000 years of history. So that's a perplexing thing. We know that we've been adding CO2 to the atmosphere in really huge amounts, and we know that can't be a good thing. But we're a little bit baffled about the mechanisms of how that global warming happens because there are so many positive and negative feedbacks. This slide illustrates the Earth's radiation balance, and there are figures just like it in your book. Looking at this total balance, we know that there's a really delicate balance required for life. Look at this number, 342 watts per square meter. And in a previous lecture, I showed you a chart by the IPCC the UN's Organization on Climate, that said that the total impact of all anthropogenic activities on the radiation balance is only 1 or 2 watts per square meter. So it's not a huge part, not the majority of the radiation, but it is an increase by a measurable amount of energy. So Earth's atmosphere is what's driving this warming trend. And the primary cause of warming is likely insolation patterns, but a secondary cause may be the greenhouse gases. The Earth's overall average equilibrium temperature, it changes only slightly from one year to the next. Here's the diagram from your book. We know that for radiant energy, Earth absorbs 147 units, radiates 117 with a 30-unit surplus. The atmosphere absorbs 130 units, loses 160 units for a 30-unit deficit. So this is a balance.